In this video, we're going to be solving an example problem using both conservation of momentum and mechanical energy concepts. When we do a problem which involves both momentum concepts and energy concepts, it's important that we remember to use each of those principles when it is appropriate to use it, and also to keep our work organized so as to help us make sure we are not mixing everything together. To help guide us through this process and make sure we keep everything organized and on track, we're going to be using this handout, Procedure 7, which is available at the module introduction page. You'll notice that on this handout, I've listed several different equations we can use, and as we go through this type of problem, it's going to be important to remember when each of these principles applies. So I'm going to go through this briefly, and then we're going to get into the problem. So first we have conservation of momentum. Conservation of momentum applies when we have a system of objects, and objects in that system exert forces only on each other, and we can neglect all forces acting from outside the system. Then we have conservation of mechanical energy. Conservation of mechanical energy applies when all the forces acting are conservative forces. And then finally, we have this one, which says change in kinetic energy plus change in potential energy equals work done by non-conservative forces. This statement is always true, but we can't always use it because very often there are non-conservative forces acting, and we have no way of directly computing the work done by those non-conservative forces. And if we can't directly calculate the work done by the non-conservative forces, that can render this equation useless for what we're trying to do. So anyways, let's look at the problem here. In this problem, I have two masses which are able to move on a frictionless horizontal surface. Initially, I have mass 1 moving to the right. Mass 2 initially has a velocity of 0, and mass 2 is attached to one end of a spring, and then the other end of the spring is fixed to a wall. What's going to happen is that mass 1 is going to come in and collide with mass 2. After the collision, mass 2 is going to continue to the right, thus compressing the spring. And the problem is asking us, first of all, what is the velocity of mass 2 immediately after it collides with mass 1? And then what is the maximum compression of the spring as mass 2 moves to the right, thus compressing the spring? We are given the masses. Mass 1 is 3 kilograms. Mass 2 is 7 kilograms. The initial velocity of mass 1 is 6 meters per second. And then we are given the spring constant, which is 285 newtons per meter. So let's go to the handout now. Step 1, it says diagrams. So part A, draw a diagram illustrating each situation of interest. Now, one thing we have to figure out here is what are the situations of interest that we want to sketch. Now, anytime we have a collision, we will always have one moment of interest immediately before the collision and one immediately after. So what's going to happen here is that mass 1 is going to come in and collide with mass 2, and then the masses are going to separate. That's a collision. So we have one moment of interest immediately before the collision. So I have just labeled this scenario A. Then we're going to draw in another moment of interest immediately after the collision. Now, immediately after the collision, mass 2 is already moving to the right at velocity v2b, but it has not had a chance to actually go anywhere yet, so that the spring is still at its original length. And I left out before that the spring is starting at its resting length. And let's put in mass 1. We are told that after the collision, mass 2 rebounds to the left. So let's call this velocity v2b, or v1b rather. So this whole thing here is situation B. So we have one moment of interest right before the collision, one right after. And then our last moment of interest will be with the spring at the maximum compression. Okay, so let's draw that spring scrunched up a bit. Spring constant K, mass 2. Now in situation C, I'm not going to even bother to draw mass 1. Mass 1 already did its job, and then after the collision, mass 1 just keeps moving to the left. We don't care about it anymore. Actually, let me also go into the figure and indicate the compression of the spring. Let's call that compression X. Right, now, what is the velocity of mass 2 at the moment that the spring is maximally compressed? Suppose mass 2 is moving to the right. If mass 2 is moving to the right, that would mean that we had not yet reached the moment of maximum compression, right? If mass 2 is moving to the right, it's still in the process of compressing the spring. On the other hand, suppose mass 2 is moving to the left. If mass 2 is moving to the left, that would mean that we had already missed that moment of maximum compression. So what is the velocity of mass 2 at the moment of maximum compression? That must be 0. So I'll just come in here and say that the velocity of mass 2 in situation C is 0. Step C, it says introduce a 0 level for gravitational potential energy. Now we don't need to do that here because there is no vertical motion. All of the motion here is horizontal, so we don't need to worry about gravitational potential energy. Step 1D, it says introduce a coordinate system. Now, all we really need the coordinate system for is to keep track of whether the velocities are going to the left or right. So I'm going to come in and just put a positive x direction to the right. And that's really all we need for the coordinate system. Okay, now we get to step 1E. From each transition from one situation to the next, write down which physical law applies. So this is the part where we really have to be thinking. Let's figure out which physical principle applies as we go from moment A to moment B. Well, first of all, can we use conservation of mechanical energy? Well, we can't, and the reason for that is that during the collision, those masses exert forces on each other, and those forces may very well be non-conservative. If the masses are exerting non-conservative forces on each other, those non-conservative forces may very well be doing work. And if we have non-conservative forces doing work, conservation of mechanical energy is out the window. Okay, what about this last option? Well, this last option, change in kinetic plus change in potential equals work done by non-conservative forces. This will actually be true, but it doesn't help us because we have no direct way of calculating the work that those non-conservative forces do during the collision. So that doesn't help us. How about conservation of momentum? Conservation of momentum applies when we have some group of objects which exert forces only on each other, and outside forces can be neglected. Right? So during the collision from A to B, we assume that the forces the objects exert on each other are so strong that outside forces can be neglected, and so we can use conservation of momentum. Okay, so from A to B, we're going to say total momentum in situation A equals total momentum in situation B. So we'll come back to that. Okay, what about from B to C? Okay, as we go from B to C, can we use conservation of momentum? As we go from situation B to situation C, the system that we're interested in is mass 2 in the spring. Are there any outside forces acting on that combination of mass 2 and the spring? Yes, the wall is exerting a force on the spring, and because of that, conservation of momentum is out the window. How about conservation of mechanical energy? Well, as we go from B to C, the only force acting is the spring force, so conservation of mechanical energy does apply, and everything's moving horizontally, so we're going to ignore gravitational potential energy. So as we go from B to C, we then have change in kinetic energy plus change in spring potential energy equals 0. So I will let you read through step 2 here on your own. But basically what we do at this point, after we have written down the correct physical principles, is we just apply them in the same manner that we practiced using these in the earlier modules. So let's go to this A to B step. We're going to need to write down an expression for total momentum in situation A. And we will need to write down an expression for total momentum in situation B. So here I would invite you to try this on your own. And then after you've done that, maybe even go ahead, set total momentum A equals total momentum B, and then solve through to get the velocity of mass 2 after the collision. Then rejoin the video. Okay, total momentum in situation A, mass 1, V1A. Total momentum in situation B, mass 1, V1B, plus mass 2, V2B. Now, V1B is actually given because it tells us that after the collision, mass 1 is moving to the left at 2 meters per second. So V1B must be minus 2 meters per second. It's tempting here to write this momentum as minus m2 v2b, but remember that we have a minus sign in the velocity itself, so we don't want to overdo it by putting another minus sign here. Okay, now we set total momentum in A equals total momentum in B. So we have m1 v1a equals m1 v1b plus m2 v2b. So we're solving for v2b. Okay, solving for v2b, let's take that first term, move it to the left, or picks up a minus sign. So we have m1 v1a minus m1 v1b over m2 equals v2b. All right, so I'm going to switch sides. And as I switch sides, I'm going to pull out the common factor of m1 in the numerator. So I have then m1 v1a minus v1b all over m2. Now substituting m1, 3 kilograms, v1a, 6 meters per second, then minus 2 meters per second. Divide by m2, 7 kilograms. This gives me v2b equals 3.43 meters per second. Now let's go to the B to C step, where we're going to use conservation of mechanical energy. Since we're going from B to C, what we need here is for situation B, kinetic energy in B, and spring potential energy in B. For situation C, we need kinetic energy in C and spring potential energy in C. So why don't you pause the video, fill out these 4 things as well as you can, and then maybe even put that back into mechanical energy conservation. See if you can get as far as actually solving for the maximum compression of the spring, and then rejoin the video. Okay, as we go from B to C, we're going to ignore mass 1. Mass 1 already did its job. So the kinetic energy in B, that would just be kinetic energy of mass 2. So I have 1/2 mass 2 v2b squared. In situation B, the spring has not started to compress yet, so potential energy 0. In situation C, in situation C, we have momentarily come to a speed of 0. So kinetic energy is 0, but then we have spring potential energy. The potential energy of a spring compressed through a distance x is 1/2 spring constant times the compression squared, or 1/2 kx squared. Okay, now let's put that into here. We expand the deltas. Since we're going from B to C, then instead of final minus initial, we're going to have value at C minus value at B. Same for potential energy. equals 0. All right, what's 0 here? Spring potential energy in B is 0. Kinetic energy in C is 0. Then we have minus kinetic energy B plus spring potential energy in C right? We can multiply through by 2 to get rid of those factors of a half. Now I'm going to take this first expression and move it to the right where it picks up a plus sign. So we have kx squared equals m2 v2b squared. All right, now I divide through by k and take the square root. And that's going to give me x equals m2 v2b squared over k, square root of the whole thing. Now we're going to do the substitution, and this will be an excellent opportunity to practice some unit checking as well. So M2, 7 kilograms. V2B was 3.43 meters per second, then squared, divided by K, 285 newtons per meter, then square root. Putting everything into my calculator, I got 0.538. Now, since we're solving for a distance here, we would like this to come out to be meters, but let's make sure. So in the square root here, we have in the numerator kilograms times meters squared over seconds squared. Now in the denominator, we have newtons. Newtons is kilograms meters per second squared, but then also in the denominator meters. So meters cancels meters down here. Kilograms cancels kilograms, second squared cancels second squared. So all we have remaining inside the square root is meters squared, but that square roots to meters. So we have as our answer that the maximum compression of the spring is 0.538 meters. And now we have solved an example problem using both conservation of momentum and conservation of mechanical energy.